In this presentation, we will be describing Suometry's omnipolar platform and the SDK that comes with it. First, we will present Suometry's two developer kits. Then, we will describe the SDK and sample software that comes packaged with them. Finally, we will show you a few demos of the SDK's capabilities and explain how we built them. So, what is the omnipolar platform? It's a software platform that is geared towards real-time processing of 360-degree material. The SDK provides simple functions to stitch 360-degree stereoscopic video from as little as 3 cameras. Using a fourth camera, it can provide a panoramic mono feed that comes with a live depth map. This 360-degree support is useful in situations where traditional, low field of view solutions are too costly or complex to integrate. The omnipolar platform's geometry keeps computation and latency costs low. The entire SDK can run on a mobile GPU such as NVIDIA's Jetson AGX Xavier. The SDK was designed to make it easy to migrate existing applications that use forward-facing pinhole cameras to Suometry's fully panoramic platform. It provides functions to extract planar projections from the 360-degree spherical images so that they can be presented to existing neural nets or algorithms that were trained on pinhole camera images. In the same vein, one of Suometry's philosophies is to support off-the-shelf components to allow users to tune camera rigs to their own needs. Suometry's SDK is in no way limited to what comes with the developer kits. The software supports omnipolar geometries of different sizes, baselines, fields of view, and resolutions. The Suometry SDK is simply a library of Suometry's image processing functions. Its API is modeled after Microsoft's Connect for Azure SDK, which should simplify the migration of existing applications. The SDK allows the user to select a set of sources to capture images from, and then merges these images into one of two output types: a 360-degree stereoscopic video feed, or a panoramic mono feed with a corresponding live depth map. The SDK also contains other functions, such as image reprojection or 3D point cloud reconstruction from the depth data to facilitate the migration of existing applications to Suometry's 360-degree content. The SDK currently supports 3 platforms. The version on the developer kit supports Linux on the Jetson, but for applications requiring higher performance, the SDK also runs under Linux and Windows on PCs. Speaking of PCs, it's worth mentioning again that the SDK is designed to be camera independent. It can be used with any set of cameras respecting the omnipolar geometry, so we're not limited to those provided with the developer kit. Any application engineered on the developer kit can be ported to production systems tuned to the user's requirements. Suometry has successfully created PC-based designs that use USB sensors and even compressed video feeds from security cameras. Let's take a closer look at the sample software that Suometry provides. Utilities are standalone applications performing common operations such as recording, displaying, or streaming videos. The source code for these utilities is provided, so they can be modified or adapted. However, they are designed to be immediately useful out of the box. Examples are short programs that focus on different aspects of the SDK. They are used for learning. Demos are interactive programs that demonstrate the real-time capabilities of the SDK. Finally, the samples come with a common directory that contains frequently used functions shared by the previously mentioned applications. These functions serve as a bridge between the SDK and third-party libraries such as GStreamer and OpenGL. They help accelerate prototype development by providing the infrastructure for the applications. So, enough with the slides. Let's take a look at the SDK in action. In this first demo, the camera transmits a stereo video stream. The left eye is stacked over the right eye. Notice how the frisbee appears to curve in this scene. This is because of the equirectangular projection, a popular projection for delivering stereoscopic material. So, how did we achieve this? The first thing the program does is set up something called a Suometry SDK device. The device consists of a selection of video sources and a pipeline to merge them together. In this application, we chose a pipeline that performs stereo stitching. The application then passes the stereo video feed to GStreamer. GStreamer is a third-party library used to create video pipelines. It provides a vast number of services such as encoding and video conversion. Here, we use it to encode our stereo video feed and make it available via a real-time streaming protocol server. To perform the demo, I set the server up and then connected to it using an RTSP client on my computer and recorded the video from there. You can also use GStreamer to record directly on the camera if you want. Here are some of the SDK and sample functions used to implement this application. The SDK is very flexible and contains many functions for customizing the input types, but in the context of the developer kit, the same functions and parameters are called over and over again. To reduce the clutter in your program, these common scenarios are encoded in helper functions, like the one at the bottom left, that creates a standard stitching pipeline. The functions in the middle box are used to get the processed images from the SDK. These are called over and over again in the main program. Finally, the box on the right shows the sample functions used to create a GStreamer application and connect the SDK to it. In the live depth demo, the SDK uses 4 synchronized video feeds to create a live depth map accompanied by its corresponding video. For each pixel in the depth map, there is a corresponding RGB point. Here, the application colorizes the depth. Red is closer and blue is farther away. As you can see with the person who's walking from left to right, this feature captures the camera's entire environment. To achieve this, the program once again creates a Suometry device, but this time it uses a depth pipeline. This pipeline delivers spherical or fisheye images, so to get the undistorted image like you saw in the demo, we used the SDK's reprojection feature to create cylindrical reprojections. Finally, we composited the images together using OpenGL and passed the result to GStreamer. The point cloud demo once again uses the camera's depth capabilities. This program takes a single snapshot of the camera's environment, which consists of a color image and a corresponding depth map. This information is then passed to the SDK's 3D reconstructor feature to create a 3D point cloud. In this example, we configure the SDK to provide a mono image and a depth map. The application also uses the SDK to create a 3D reconstructor, which takes the output images and turns them into a point cloud. The function calls in the left and middle boxes are very similar to those from the previous examples. The bottom right box shows the functions needed to create and use the 3D reconstructor. It also shows a sample function to save the point cloud to a PLY file, which is a common format used to store point cloud data. This point cloud can then be loaded in programs such as MeshLab to visualize them. The reprojection demo showcases the SDK's ability to distort the fisheye image into a format that may be more convenient for your application. In this demo, we capture a single camera feed and use the SDK's reprojection functions on it in real time. The video starts with an unmodified fisheye image from the camera, and then we see various reprojections supported by the SDK, such as a cube map, or cylindrical reprojection, equirectangular, equisolid, and planar. Planar is particularly interesting because it takes a warped fisheye image and undistorts it as if the image had been taken with a pinhole camera. Notice the straight lines on the arbor and the railing. Planar can be useful in situations where a fisheye image is impractical. Take, for example, an AI model trained to recognize objects in standard images taken with a pinhole camera. It would have a hard time detecting such objects in fisheye images. By creating a planar reprojection like this, it's possible to make use of such algorithms. The Suometry SDK also contains functions to translate between projections, so a point of interest found in one projection can easily be found in another. The Suometry SDK device used in this application is simpler. We don't use a pipeline, we simply capture. This demo also feeds into GStreamer, but this time it uses it to simply record to disk. Once again, we see the familiar functions to set up the device and recover images. However, the device is only used for capture and is created without a pipeline. The bottom right shows functions used to create a reprojector, which converts from one projection to another. In this demo, we instantiate many of these reprojectors and switch between them. If you want to know more about the functions mentioned in this presentation, HTML documentation can be found in the /opt/suometry/doc directory that comes with the camera. Thanks for your attention. If you have any questions, please visit suometry.com.